Okay, welcome to our Accelerating Generative AI. This will be a panel session that we're going to run and talk about the various ways that we want to conquer the bottlenecks that can occur and how we can move generative AI forward. We're going to cover a lot of topics from processors all the way through the network, storage, memory. And let's go to our panel here. Go ahead and go to the next slide, Diane. I'm Dave Eggleston. I'm from Microchip, and I'll be moderating today's session. And we're going to walk through each of our presenters. Got a great panel for you here today. We have Mario for AMD. Say hello, Mario. And go ahead and wave. And Rob Davis from NVIDIA.
Hey, guys.
David McIntyre from Samsung, also on the SNEA Board of Directors.
Greetings, everyone.
And Andreas Rodriguez from Intel.
Hello.
And Joe White from Dell.
Hey, good morning.
And thanks for everybody joining us today. We are being sponsored by SNEA. SNEA is a great organization that covers all kinds of topics, including this topic of generative AI. If you have questions throughout this session, you can go to the upper right corner where you see the question mark and type in your questions while we're talking. And we'll certainly try and get to some of those questions. I do expect this panel to run for most of the hour, so I don't know that there'll be time at the end for Q&A. As you can see from SNEA, a lot of numbers up there, but let's jump into the content. Of course, I'm not a lawyer, and I don't even play one in a webinar. So this is the legal notice, and you can see, use at your own risk. I think that's the only thing I'll say. All right, next slide. Let's get started and let's show all those smiling faces. Thanks, guys. And let's start off with the very first question. What are the bottlenecks that you see for doing generative AI? And again, that can be anywhere in the system. So let's start with Mario. Mario, from your perspective, what do you see as the bottlenecks?
Well, given that that's what I work on, the first bottleneck I see is certainly the network, but it's not only my point of view. It's really clear that today, where we are trying to build very highly distributed systems for training and even for inference, the exchange of the amount of data that needs to be exchanged between the hosts is huge. And so the network is really where, in many cases, we get limited in our performance.
I'm feeling that pain today because I'm having network bottleneck issues even during this webinar. So if I should drop off, Dave McIntyre will be subbing in for me. But yes, the network can certainly be a place where we have to be concerned about the bottleneck. Okay, Mr. GPU from NVIDIA, Rob Davis, I guess you also represent some other things as well. But tell us about what the bottlenecks are from your point of view.
Sure. And it depends on the AI application, of course. But the bottlenecks can be in the compute, the memory, unoptimized software, or as Mario said, the I/O. So an I/O example with a little more detail, with Gen AI, often the data set you are training with or the live data you're inferencing with is either too big to fit in the local storage of the GPU server, or the problem is too big to fit in one of the GPU servers. In these cases,
and how big are these models? You know, give us some idea what you're seeing these days, Rob.
Sure. So, for example, for large language models, maybe 5-ish years ago, the number of parameters that went into one was about 200 million. And last year, it was over 1 trillion. So enormous models. And again, it depends on the application, but very big.
Yeah, let's have Andreas from Intel speak to that. Andreas, give us your view too. What are some of those bottlenecks we need to be thinking about?
So I have a bit of a different perspective. There are a few very large companies, internet companies in particular, that are training these extremely large language models where network is one of the main bottlenecks in the training process. But if you look across the ecosystem, you see that the majority of the deployments that enterprises have are leveraging the smaller size of the large language models these companies are not training these extremely large language models. They are often fine-tuning them, which requires much less compute nodes. And when they are deploying them in inference, they are often deploying them on a single server where network is not the bottleneck. What I observe in deployment scenarios in the broader market are models that are typically under 13 billion parameters, and 13 billion, 7 billion are common thanks to the release of the Llama 2 family of models from Meta with 7 billion, 13 billion, and 70 billion. And if you just look at the number of downloads, you see humongous downloads and applications centered around the 7 billion parameters, where these models run very well on a single server. Now, that's not to say that the trillion plus parameter models are not important. It's just that their adoption are very limited to just a few
So you're
companies.
helping us understand there's this whole spectrum of applications in generative AI, some of which do require GPUs and lots of memory and storage and a very fast network, but some of them don't. So in some of those systems that you're working on, what do you see as the bottlenecks? I know you work on software, and is software a bottleneck at times?
So the main gap that I see is the growing gap between compute and memory bandwidth. So we continue to increase the amount of transistors that we can put in silicon, resulting in much more compute, but memory bandwidth is increasing at a much lower pace. This is no secret in the community.
Between compute and memory. So let's jump to Dave. Dave from Samsung. Samsung's a big supplier of both memory and storage. He says you got a problem with your memory bandwidth, and what are you going to do about that?
We actually don't have a problem with bandwidth because we have a very stellar roadmap around our HBM products. I will say that Samsung is a leading supplier of memory and NAND flash components, has now graduated into a solutions company. And this is it's a very exciting challenge for Samsung. Of course, we've been in the solutions business across the whole sphere of different applications, but specific to what we're talking about here, it behooves us to look at the correct balance between memory, storage, and compute resources to work through the balancing of LLMs and eventually reduced size language models at the client side. I think, we've talked maybe 2 years ago about cloud deployments to IoT to endpoints out in the field. Well, Samsung has the resources to support all of those types of infrastructure deployments and around applications in LLMs in the data center, on-prem, in cloud, and also out at the client sites too.
So what do you see as the bottlenecks? Definitely HBM is widely used with the GPUs, but where are the bottlenecks from?
So what we've seen the bottlenecks are, and it is a good point that going through the compute resource and memory resource balancing to provide the insatiable demand of more bandwidth, that's where HBM can come into play. There's also the bottlenecking on capacity itself, which can be supported by new technologies like CXL, which I'm sure we'll talk about a little bit later.
Thank you. And my bottleneck of my network is playing tricks with me here. Joe, let's switch to you at Dell. I mean, you have to pull all these pieces together and answer the customer's needs. So how do you see it? For generative AI, where are the bottlenecks that we need to focus on?
Yeah, so basically we see bottlenecks at every interface between components. So you heard all my colleagues talk about the various individual pieces and individual bottlenecks, and we see all of those. But really, if you take an end-to-end view, every interface has a bottleneck or potential bottleneck. And the complexity is driven by each model in each size of data set and each size of model and how much you want to distribute it and how fast you want the training to be depends upon which training you're doing. So if you're training one model versus another, you get a different set of things that are important. If you're doing single node versus multi GPU node versus sort of distributed or disaggregated scale out, you have different bottlenecks. And as all of my colleagues said, there are ways to solve sort of each of those bottlenecks individually. There's a trick in pulling them all together, and you can do it, and we're all working on it, but it becomes quite a bit more complex. So you don't just run one network, you run 3 or 5 networks, or sometimes a lot of networks. You don't just run one memory interface one place. You've got to scale that the width of the memory and so on. You don't just run, oh, I've got some storage out there. No, you've got to do direct access to local storage plus remote storage and make the remote storage look like it's local. You don't just run any old software. You run software that has optimizations in it to use the network and the storage and the GPUs more directly and more effectively. So to us, it's about building infrastructure that can be flexible across deployments and then optimizing kind of that end to end for each of the kinds of models at each scale, at each training set.
So that gives us a lot of problems, and there's a lot of interfaces to solve there. And I think for our audience, what we're seeing here is there's quite a lot of diversity of opinion, and what you see is the different issues, whether it be the memory interface or whether it be the size of model or whether it's the network. So diversity of opinion, of course, of how we're seeing the problem. So let's go to, well, what are some potential solutions here? Joe, let's start with you. I mean, how do you identify where these bottlenecks are? How do we move ahead here in identifying where we can make improvements?
Yeah. So benchmarks is critical. So things like MLPerf, TPC, AI, StackML, low-level benchmarks as well, like Stream, iPerf, FIO, so that you can understand how each of the interfaces and components behave. And then once you have live deployments, having proper end-to-end visibility, observability, telemetry, profiler tools, so that you can go, oh, we're weak here, we actually need to take a different approach. Or, hey, this is working great, nothing to do there, right? And, I'll invoke the spirit of Mr. Amdahl and Amdahl's law that, heavily optimizing something that only is, 10% of the problem didn't get you much. So you need to look at where the worst parts of the problem is. That's where the tools come in. Thank you.
Got it. Let's Mario, go ahead and weigh in. Same kind of question. What are you using to identify where those problem areas are and potential solutions?
Yeah. I think Joe really touched upon one of the things that I think are more important, which is getting data about how your jobs are running. And I agree with Joe. Benchmarks are important, but it's really very important also to be able to monitor what's going on with your jobs as they are running, because we are dealing in some cases with systems that are so large, which is impossible, impractical to reproduce them just to run some performance analysis. So we need to do that as the jobs are running in production. And I think here's where really the software is crucial. Of course, we need also capabilities in the hardware to provide the right telemetry. But then it's the software. It's important to have the right software to collect the telemetry and also to instrument the software at a higher level. So, for example, the libraries, the frameworks that we use to build the applications to log whatever information is critical to us, because we cannot rely too much on fine-grained, low-level information, because it would be a ton of information, and then it's going to be very hard to process. Instead, One approach is to instrument the software to immediately help us to identify bottlenecks without creating huge logs that then we have to go through, because that would be absolutely impractical. And
So let's jump to Andreas. Sorry to interrupt there, but these are some of the ways we can identify where those problems are. Andreas, you brought up an important concept that we have many different ways, many different processors, whether GPUs, CPUs, ASICs, DPUs, XPU, all kinds of solutions here. How do we know? How do we match up? What's the right processor for the job, right processor for the workload we're trying to handle? How do we determine that?
So somebody mentioned benchmarking, and I think that's a step. The challenge that I see with the traditional benchmarks is they are looking at models from the past. So like the MLPerf benchmarks has ResNet 50 from 2015, which is a dinosaur compared to compared to the AI field. So we need to be monitoring the ecosystem, working closely with enterprises. What are they deploying today? What are they looking to deploy tomorrow? And it's going to be quite different from most of the benchmarks that are in most of the workloads that are in these benchmarks. You also ask, hey, what are we doing to improve the performance to resolve these bottlenecks? And we're doing a number of things, from improving the process technologies, moving from 4 nanometers all the way down to 18 angstrom in the next few years. We're working with the software ecosystem, with PyTorch, with TensorFlow, with the MLIR community, to make sure that those libraries are well optimized for the various hardware backends. And you mentioned a few of the hardware platforms that are available. And we also work on algorithmic innovations. So how do you quantize better? How do you use lower precision? Because that requires less power. You can put a lot more compute. How do you take these very large models and distill them to small models that give you the same or almost the same exact accuracy as the large models, but requiring significantly less compute, bandwidth, network, etc.? How do you improve the communication collective primitives to efficiently implement like the all-reduced algorithm, which are important not just in training but in inference? So we're looking at the whole hardware, software, and algorithms co-design to be able to deliver performance across CPUs and across GPUs and accelerators.
Not sure who's next, but I can jump in. I think one thing to be considering is the time. Okay, so you can do a lot of AI on CPUs, but it might take days or years. Whereas with GPUs, typically they're much faster. And then the other thing is price. So definitely the CPUs are cheaper, but again, it comes back to the time. And then the other thing I leverage off of what Joe said about the full, every single component, right? So from the software to the GPUs or CPUs. And in the case of GPUs, remember, there's typically a CPU that's hosting that, that GPU server, and that can play into the total performance. So it's all up and down. So you really have to look at it from a full stack perspective. All the different software, all the libraries, all the drivers, all the different components.
I do want to, I feel I need to respond to the comment on CPUs taking a long time. And there are areas that CPU has done to significantly accelerate the performance. So you can do fine-tuning, even training, and certainly inference quite efficiently in a matter of milliseconds. So CPUs nowadays have a built-in systolic array, like a dedicated AI accelerator built inside of them. And the software is significantly much more optimized than it was a few years ago. So if you had tried inference on CPUs a few years ago, you would have seen significant performance lags because of the lack of optimizations and the lack of AI hardware accelerators. But today, you can definitely use CPUs for inference, for all your inference, and for even for some fine tuning and training work.
If you're willing to wait, yes.
Well,
Joe, I
Well,
think looks like you have a comment there. Why don't you chime in there?
yeah, so it depends upon the details of the model, the data set, and exactly which piece of optimization you have to run for that. So there are models where that would take an enormous amount of time if you tried to do it on pure CPUs, because what do GPUs really do for you? They do certain kinds of linear algebra arithmetic much, much faster and more cost effectively, right? The amount of operations you get per watt is just better. And the speed at which they can run is just better. And the amount of parallel pipelines they have is just better. Now, there are
And the
other
memory bandwidth is just better.
it's just better. And so there are other models where you don't really need all that. You can't take advantage of it. Okay. And there are other models that are well contained. And if I'm doing inferencing, that's an even trickier trade-off, because you're like, well, I could deploy a GPU, but there's a certain amount of stuff that goes into running and feeding and carrying that GPU. Could I just put a CPU to do my inferencing? Maybe. On the other hand, if you're trying to do heavy streamed inferencing at the edge, maybe a smaller GPU is a better device, or a CPU and GPU in combination. So it's never one thing or the other is my view and what I'm trying to point out. It's never
Or if your inferencing needs RAG, then you definitely need a GPU in the loop.
Yeah.
So Mario, let's let Mario weigh in here.
Yeah, no, yeah, I just wanted to, in fact, add or complement what you said with the fact that, in fact, the big challenge is that we are dealing with heterogeneous systems where we have different types of compute, and the challenge is really to use what's best. And in addition to the CPU and the GPU, we also may have other types of accelerators. We have these very sophisticated smart NICs today with DPUs or IPUs or however you want to call
FPGAs.
them, FPGA-based SmartNICs or FPGA accelerators, which can be very useful to very efficiently perform operations when you want to use specific data types that may not be supported by the traditional GPUs or CPUs. So first of all, true, depends on the application, but second, we really need the tools to be able to map the application or the parts of the applications to the right piece of the system. And that's really one of the challenges we have.
Got it. Let's let David go ahead and weigh in as well.
Yeah.
Please.
So you mentioned heterogeneous compute, and that's basically what we're talking through right now. What type of compute element best serves the data and the application that data needs to run under. And so there's many trades. The other is taking a look at data-centric compute from an infrastructure standpoint, where there's additional opportunities from a power savings and efficiency standpoint, where you simply don't have to move the data around as much. By intelligently architecting a system and having expansion elements in memory, such through CXL, we can now, instead of brute forcing the problem, we can come up with a more, almost like as an artist, come up with the best painting of an infrastructure solution that provides that sustainability benefit.
So David, you're talking here about moving the processing closer to the data.
Yes.
Is this the right approach, or moving the data closer to the processing, or is it both? Because
it's both. Yeah.
So depends, like always, on the application, right? If it's something,
does.
Yeah.
So Rob, give us some examples. When does it make sense to move it one way versus the other?
Well, if it's compute at a distance, like say you were a large store that had video cameras and you were watching all of the you had an AI application that was looking for people that were stealing from the store, you would definitely need that to be local. You couldn't have that going back to headquarters, right? Whereas if you were using that data to see where people's eyes went most, so you could sell the shelf space for more, that's data that you'd want to run on your data center, back at headquarters to figure out where you're going to put the shelves. So that would be kind of an example.
Joe,
but
looks like you want to weigh in.
I think there's
please.
a distinction here between data locality relative to core versus edge, or cloud core versus edge.
Yeah, expand on that.
Versus where you put the processing in the infrastructure elements itself. So in other words, do I have a storage array
And
that
the data.
in capabilities, or do I have compute capabilities, which is GPU plus CPU plus DPU, IPU, right? Do I have compute capabilities? And then do I have storage? Because I can never put the right amount of compute directly on my storage. That's always a lose, except for very specialized cases, so there'll never be volume there. Or is it that, hey, that compute on storage is general enough that it can do certain transformations for you much more effectively than moving the data, transforming it, moving it back, and then moving it to where you use it for training. And I don't think we've converged as an industry on which way the future is going to be. And
how do we do that?
Really,
how would we converge? Yeah, give us your thoughts, sir.
I mean, how does the industry converge on that? It's going to take people trying it, and we'll see what sticks.
Build stuff and see what happens. Let's look at Andreas here.
There's no first principles or a priori answer to that one. We can't calculate it. We're going to have
time,
to try.
But time is definitely the major component.
Try things out. Try innovative experiments. Okay, Andreas, same line of thought. Moving data closer to processing or processing closer to data?
So I think it depends also on the application, where you're doing training or whether you're doing inference. Of course, when you're doing training, you have the need to read extremely large amounts of data. So having the data very close to a compute is beneficial. When you're doing inference, it's different. The amount of data that you process is significantly smaller. So the requirements are different. I did wanted to just go back to one point that was mentioned earlier, that in CPUs you have to wait a long time, and just to reiterate that's no longer the case. In CPUs, large language models can be deployed in inference in a matter of milliseconds, and this is in part because of the accelerators and software optimizations. And when you are deploying models, you typically are not using the very large batches that you process during training. Large batches are very easily to parallelize, and having a dedicated accelerator like a Gaudi or a GPU would be very beneficial for training, because you can parallelize all that across the available compute. When you're doing inference, you're processing one or few samples at a time, which can be parallelized depending on the model that you're using, but it's much more difficult, and you have a lot more single operations that will benefit from the higher core performance. As somebody mentioned, Am's law, it's going to be harder and harder to parallelize smaller. So it's a good platform for particularly for inference, real-time deployments.
So David, you started off this section of our chat here talking about, in particular with memory and storage, how moving compute close to memory and storage, or actually integrating it with memory and storage. Maybe give us a little bit more on that and your views of what's the trend there and how that helps solve this generative AI bottleneck.
Yeah, so SNIA has a working model for computational storage, as well as a programming model that complements how SNIA defines computational storage. What I've learned over the last few years is that computational storage is not an island. It can't be. We have to look at memory as well as storage and compute holistically. And the latest trend now is bringing in memory as a primary player for memory tiering, memory caching, and even memory persistence. And I mentioned CXL earlier. That is a really exciting technology area because most companies are embracing those 3 protocols that run on PCIe Gen 5 and shortly Gen 6 on 3.1. And so there's an opportunity there to expand upon what computational storage means into what I alluded to earlier as data-centric compute. So by looking at not only the bottlenecking problems, but the efficiency problems on performance per watt basis, using these puzzle pieces or building blocks across those resources is a very exciting time. But I do see the challenge here graduating from infrastructure efficiencies to marrying up with the applications themselves. And that's where software also plays a very primary important role.
Got it. Okay, let's see if there's any final comments, on this topic of where to move the processing. Go ahead, please, Mario.
If I may, I wanted to add another dimension to this, moving computation to the data and vice versa, which is computing the data as it moves, right? I mean, where it applies and where it can be effective. I mean, I was mentioning before, we have quite powerful and efficient processing capabilities, for example, in SmartNICs and in switches, right? We are, especially, for example, for offloading the computation that needs to be done during the collective communications, where you need to aggregate or reduce data that then needs to be redistributed to a number of workers. So that's a computation that can be efficiently done at the network edge in the NICs, SmartNICs, or even in the switches. It can be very, very efficient. Of course, this requires, however, to have computation capabilities that are not typical of those devices. I was saying we have devices that are powerful, that have powerful computation capabilities. They are programmable, but traditionally those computation capabilities are designed for a type of processing that's typical of protocol processing, packet processing. Here we need a slightly different type of processing, but that's definitely a spot, the network, where performing certain computation can be very efficient, and consequently adding those computation capabilities that are needed may be very cost effective.
So let's jump to Rob. Yeah, go ahead.
That's already done in InfiniBand switches today, at least the ones from my company. And I agree with you, the DPUs are another perfect place to start thinking about that from Ethernet perspective. And
expand on that a little bit more, Rob. Why is that the right place?
Well, because the CPUs and GPUs are dedicated to the AI applications, right? And what DPUs are designed for is to offload, accelerate, and secure basically the GPU server, or a regular server for that matter. And you've got a lot of ability to accelerate AI applications with offload engines built into the DPUs, or RISC processors or ARM processors, basically very focused applications that don't have to worry about the general CPU. And they're connected to high performance networks, and they have PCI switches. They're basically little servers plugged into the main GPU server or regular CPU.
Got it. Joe, please weigh in.
You think about the operations you have to do to both do training and inferencing for these models. And if you go to first principles, you essentially have data feed, data transformation. So I want to scale my data or do some other arithmetic to it. I have aggregation or fan in and fan out, where I combine parameter sets together with fairly simple arithmetic, or then I fan them out. And if you look at which element is good, and then I have general purpose sort of computation, and then I have linear algebra stuff. And if you look at it that way, each of the different elements or devices that my colleagues have been talking about do a piece of those, one of those jobs really well. So what does a DPU or a logic unit in the middle of the fabric do? Well, it can take packets in, combine them, and send them out, or it can replicate them and fan them out really well, or it can do scaling on the things. What can in storage compute do? It can scale data, or it can filter and search for data. What can a GPU do? Linear algebra. What can a CPU do? Any of those things, but it's never really the best at any of those operations, but it can do them all. And people aren't really just building CPUs anymore. As my colleague Andreas said, what they're really building is optimized processors for future workloads, because they're combining some GPU-like things, some other acceleration with traditional CPU, and that combination can often be very effective for some class of models. And so again, it's never a one-size-fits-all. I mean, part of the complexity and mess here, especially if you're trying, companies like all of ours, trying to build this stuff for people to use for some interesting application, like making a health advisor bot. That is really good.
So let me interrupt quickly. I mean, we're starting to get the questions roll in. So if somebody wants to ask a question.
One last thing on the DPU is that it can
ahead.
also help fix the bottlenecks in the network, because it's connected directly to the network and doesn't have to rely on the operating system and interfaces to CPUs and whatnot. You can do things like advanced congestion control, and these are things on standard Ethernet. You can do things like congestion control, adaptive routing, right between the DPUs and the networks to optimize that network traffic, which gets super heavy when you're doing, very intense AI applications.
Yeah, you can also prepare the data to optimize the communication. Like, you can work on compressing or using specialized techniques that are encryption for sure, for security. And you can, leverage sparsity, for example. So that's really a very important element.
And it fits great into what Joe was saying. These different pieces are really good at what they do. And if you can optimize a full stack solution with each of those pieces being optimized for whatever their expertise is, you really have, the best top to bottom answer.
So Rob, one of the questions here, and Joe and Andreas, it says, hello, does that mean a GPU is more efficient to use than the CPU and DPU? Joe, go ahead. You're shaking your head. Go ahead and address that.
If somebody asked me that exactly that way and I had to give a yes, no answer, I would go no. If they inverted the question, asked it the other way, I would also give no. So there is no single answer, which is part of why we have this webinar going. There is no single answer to that question. Right, so it's all
depends on the application.
All it depends. Now, the ideal would be you could have a clump of infrastructure as a whole, disaggregated infrastructure that had software that could use each of the elements the most efficiently, had software optimizations built in, a beautiful end-to-end system where you sort of gave it a high-level problem statement and it spit out a model that you could then feed data to and get answers.
Should we ask ChatGPT?
But we're not there yet, and we're all driving towards that.
Got it. Andreas, go ahead and weigh in on the same question.
Yeah, so the challenge that we have, particularly in the large language model space, where we've seen explosive growth over the past year, is there is no single hardware that excels at both phases of large language models, and there is inefficiencies at both ends. So the two components of large language models is you process the input, and this is a very compute intensive operation, and then you start generating the text or the tokens, and this is a very memory bandwidth intensive operation, because for every token you generate, you typically have to read the entire model from memory, and the model can be quite large in some cases, but even the smaller language models are still quite large. And so you have to move all this data around, and the compute capabilities of your CPU or your GPU are low utilization during this phase. And so it's a really great challenge, I think, that hardware vendors have in being able to do our best job in predicting the future and how the hardware components are going to be stressed to be able to make the right design decisions to provide the market the best balanced platform that we can possibly provide. But it is there are going to be inefficiencies because models are going to be stressed in different parts of the AI system design.
So one of the specific questions that came in is about the GPU to GPU interface. And our friend Danny asks about how does NVLink or other proprietary GPU to GPU interconnect address bottlenecks? Why is the industry focused on 8 GPU deployment versus 16 GPU deployment resolution, given that LLMs are not training on tens of thousands of GPUs? So anyone want to take
Sure. NVLink is designed to allow the clustering of the GPUs and the memory to be shared between the GPUs. And it's, super high performance, more high performance than any of the networking technologies that we support, InfiniBand or Ethernet. And but it does have limited scale. It's, we're expanding that scale. But anyway, the main purpose is to allow the GPUs to share memory so that we solve that memory problem that was brought up earlier. And then, of course, you get an advantage with the clustering of the GPUs for very large problems as well.
In chassis, so the 8 versus 16 versus 32, the chassis and box design is all just practical limits. It's not driven from any first principles reason. It's just what can we put in a piece of sheet metal and have operate together with the limits of the PCI going to CXL switch sizes, with the limits of the number of pins you can bring out, with the limits of the bandwidth connectivity on each of the interfaces we talked about.
And the power and cooling.
I was going to say power and heat.
And then the rack design. So it's all just practical arithmetic. And where the future is going to go is interesting. So there are standards like OpenRack v3, which are going to change things. There are significant power and cooling trends that you can look up that will change things. A box with 8 GPUs in it and local connectivity, all practical. If I could have 32, I'd be happier. If I could have 4 to 64 in a rack, super flexible, I'd be happier. But practically speaking, there are trade-offs, and that's why you see those numbers.
And NVLink has no limitations within the parameters that Joe just went through. It can do a rack.
And in point of fact, the optical signaling for all of the networks that are out there, even if you were talking about building a CXL network, the bit rate on the lines and the distance on the lines themselves is the same pretty much across the board. The amount of bandwidth and the way you construct your network topology is a complex thing, and again, full of trade-offs. And I know I keep saying that, but it's just, I want you to take away that there's no one size fits all, and that all of the networks that we know about could all scale in principle to whatever size you want if you're willing to pay the number of switches and the number of interfaces, links it would take to do it.
And spend all the time to get it tuned and working and debugged.
Lots of practical things, but again, there's no magic in one versus the other. And if I have CXL, I'm going to run into the same kind of network problems. Distributed CXL, I'll run into the same network problems that we have with InfiniBand, Ethernet, NVLink. I mean, frankly, Fiber Channel. Frankly, 5 other networks that have been around in the past.
Ring, FDDI.
Yeah, we're revisiting the same problems, but faster.
There's a question. Yeah, sorry to interrupt here. Let's jump to Mario quickly, Andreas. I'll come back to you in a second. Mario, is there, one of the questions, Mario, is there a DPU with vector engines in it? And Rob, same with InfiniBand switches with vector engines. Mario, go ahead.
Yeah, well, as far as I can tell, I don't think so, because they are designed, as I was saying before, for packet and protocol processing. But of course, there are other solutions that you can use, like, for example, FPGAs, and there you can implement pretty much any kind of processing, any kind of operations you want. Moreover, as I was mentioning before, on the type of data, on the data types that are best suited for your specific application.
Okay, Rob, real quick.
Yeah, I'm not 100% sure of all the capabilities of the InfiniBand switches, but they're always getting more and more, and they've been doing this for years in the HPC space. But we do also have adapters. We build PCI adapters that have GPUs and DPUs on the same card. So there you get the best of both worlds.
I think David is frozen there. We can maybe move to another question.
Yeah. So just on the expansion, Joe and Rob, you said it, that there's a limitation, physical limitation on, regardless of the linking topology, there's going to be some challenges, whether it's, the previous interface we talked about or link, but there are, these links can coexist, right? So CXL is quite interesting because you have 3 protocol types for accelerators, like we talked about earlier, for SmartNIC, right? That's the type 1, and then also for memory caching. So in fact, for CXL, and Joe's right that there's only so much you can do with physics, but there is that opportunity to break beyond or expand those barriers, I suppose, starting with memory expansion and memory tiering, as well as addressing SmartNIC via CXL. So looking at the overall options that we have, I think these interfaces can coexist.
And the tuning time, right? Over time, these interfaces get faster and faster just because people learn more how to take advantage of them, how to tune them.
Absolutely.
Yeah, but I think there's also another limit to the scalability of those solutions, which is at the protocol level. Like, they are designed to build clusters that are not too large, or pods that are not too large. Once you want to go to larger pods and larger clusters, and you need to have multiple layers of switches, then you need to introduce more complexity. Like, for example, before Rob was mentioning sophisticated congestion control, that those solutions are not designed to have, and that's why they are faster and they are leaner. And that's the reason why then we have a whole set of different solutions for that scenario. And we make this difference usually between scaling up and scaling out, right?
The more distance and the more scale, usually the less performance.
Yeah, although, so in the introduction of, say, memory semantics with load store versus read write sort of, and stream semantics, I mean, all those semantics give you different appreciation of the programming model and let you abstract the hardware in different ways. And some amount of scale out memory blending into sort of transparent storage access and let some of the infrastructure handle the lower level optimizations is an interesting direction going forward.
Now, caching, you mean, Joe?
Yeah, caching or hierarchical or sort of automated movement of data to the right place so the application doesn't have to manage its own data access and data movement underneath the covers that happens. And the application just goes load, store, load, store, load, store, and that includes GPUs and CPUs. Under the covers, a bunch of complex stuff happens. Now, whether you can make that cache coherent on a large domain is an interesting, both theoretical and practical problem. But, industry is looking at all this stuff. Again, in all our various combinations of partnerships, because everyone partners with everyone, we're looking at all this stuff, and we have industry consortiums that are doing the same thing. And what that leads me to is that one of the richest places for innovation right now is probably the integration of the software stacks into the infrastructure itself, and how the software stacks optimize and take advantage of that infrastructure in a sort of a really clean way. That's kind of
so. Let's jump to Andreas to address that. He's in the software field, and I know we tabled one point you wanted to make earlier, Andreas. So I think go ahead and tackle that how to integrate the software stack into the hardware, and then also the point you wanted to make earlier.
Yeah, so the point from earlier is on the practicality of scaling beyond 8 different compute nodes. And we've looked at this also in the context of our Gaudi accelerators, our Gaudi AI accelerators, and the need to scale beyond 8 units. And while the capability is there, the practicality, particularly for inference, is much, it's not as critical. So when you have 8 Gaudi or some other cluster with 8 GPUs, you can do inference on almost every single LLM model. You have the memory capacity to do inference on the extremely large language models, up to like 200 plus billion parameters. Once you go into the trillion parameter models inference, then you are going to have to go to 32, and then you have to have the 2 jumps to be able to scale. But practically, there are very, very few companies that are deploying these large, extremely large language models. So practically, 8 seems to be a good sweet spot to cover the overwhelming majority of the market. On the second point, to integrate the software, so the majority of the market is using PyTorch, and to a smaller extent, it's TensorFlow. TensorFlow is somewhat decreasing in popularity as PyTorch is increasing. And as hardware vendors, we work with these companies to make sure that with these libraries, to make sure that these libraries can take advantage of the hardware features, both the compute and the communication features that we as hardware vendors offer. And I just think we need to continue with this tight integration between these open source libraries and us as hardware vendors, to make sure that the end users of these libraries can benefit from the acceleration that hardware vendors are providing.
Okay, now we're almost to the top of the hour. Thank you to our audience for hanging in there with us. Thank you to our panelists as well. Now we're going to switch quickly to the speed round, where I'm going to ask you to sum up in 5 to 10 words max. Let's see if you can fit into that frame. Addressing generative AI bottlenecks. How do you address the generative AI bottlenecks? Rob, let's go to you first.
Oh, great. GPU efficiency, memory, and network.
Okay,
very good. Mario.
Yeah, I would say efficiency, and this means using the right compute for the right operation.
Okay, Andreas.
Processing technology for more transistors in the same silicon area, better software optimizations to take advantage of all the transistors, and algorithmic innovations to deliver performance deliver the performance of the large language models with smaller language models, or smaller models in general.
Joe, go ahead.
So optimized software integration on top of distributed flexible hardware to solve AI problems across the variety of model types and scales.
All right, David, take us home here.
Smart and power efficient infrastructure solutions now.
All right, excellent. Okay, Diane, if you can go ahead and advance the slide to the next. Yes, and thank you again to our panelists. Did a fantastic job. Let me give them a quick hand on that, and hopefully you will rate our panel and our panelists with the top rating. There will be, my understanding is there will be a survey or feedback survey that does come out. Now, there is a next AI webinar. If you like this and you want to get into the topic more, SNIA is sponsoring another AI webinar about the hidden costs of AI, and that's coming up roughly a month from now. So you can register to join that. And we encourage all of our audience members today to join SNIA. If your company hasn't joined yet, please encourage your company to join SNIA and get involved. There's a number of technical work groups, etc., that you can get involved. And here is the link right there. And you can follow that link and it'll show you how to become a member, and you can get involved certainly by talking to any of our panelists here today, and in particular with Mr. David McIntyre, who's also on the board. So I think, Diana, if you can go back to the view where we can see all the faces. Yes, I'm sorry. One more here. Please rate this webinar and provide the feedback. And there's going to be the recording as well as a copy of any slides, which are minimal here, as well as we'll try and do some offline answers to the questions we didn't get to. All right, thank you again to all our panelists. I think if I was going to sum up in the speed round, it would be get Dave better bandwidth network, but that would be for me. Apologies to you. We're having a severe storm here today, and I've had quite a bit of trouble with that. But thanks for hanging in there. Thanks for your interest in generative AI, and thanks again to our panelists for giving us some compelling thoughts. All right, take care.
Take care. Bye. Thank you.